three kinds of lies. Lies, damn lies, and statistics. And then just for fun, 9 out of 10 people say that was Mark Twain. This is just another made-up statistic, so that's just to be funny. So standard type of computer science stuff. Here we have two algorithms. Performance, higher is better. Here is the mean of algorithm 1 and algorithm 2. Which of these is better?
Algorithm 1 is better at the mean.
You define mean as the definition of better, but if I look at the standard deviations, without parameter estimates or error bars, it's not very realistic. As a reviewer, some reviewers will call you on it. If I'm your reviewer, I will call you on it. As an author, expect reviewers to call you on it. But unfortunately, and this is why it's bad, most papers don't. Most of the papers you've probably read don't show you error bars on any of their data. It's a plot or a curve. There's no error bars. My view, and I'm trying to convince you, is that you're going to want to do this in the end because it makes your science better. Even if you don't end up showing the error bars because they make the plots too complicated, talk about them and do tests. Right? You don't have to mess up your plots and put error bars. You can replace that with mean things. So now with this drawing, which one of these do you think is better? Well, so it has a smaller variance. It tends not to go down very much at all. So variance, so actual variation in the data set. So if I did mean and variance, they would be symmetric bars. If I actually measure the min and max, they would have to be. So it depends on what the plots are.
So you have a whole bunch of things clustered around that downside.
And then every now and then it has much more topside.
Oh, that's not.
Right, yeah. So in fact, there's a whole bunch of types of plots, which we should probably stick in the lecture to as well. But a common plot is mean plus or minus standard deviation. Another is mean, min, and max. So could easily be min and max. The others I might show you mean and 25th percentile below and 25th percentile above. So and then do whisker box plots, a whole bunch of things to do it. And this comes back to, we already had this discussion, mean versus median, right? So in this data, the median might be here and the median there might be over there, right? The means are not necessarily what's driving it. So one or two really large values, either up or down, can affect where the mean goes, and so we're very sensitive to that. So my recommendation is, when you're a reviewer, call people on not having means and standard deviations or explaining them, not doing statistics, because you can't really tell what's going on. And they may or may not be doing it for a meaningful reason. Most commonly, it's just laziness. Always take the standard error account when outputting summary statistics. So quoting a silly number of decimal places, significant figures, is a sure sign of statistical and or scientific illiteracy. So if I have a mean of 10 runs of a program on a single input with times 3.01, 3.01, whatever those numbers are, so if those are the 10 numbers I'm averaging, I shouldn't report a time with 5 digits because those digits aren't meaningful, right? I only added 3 digits. So I report something like 3.1 plus or minus 0.05, where 0.05 is a standard deviation. So this is very common. You look at a paper and they'll show a table with like 5 or 7 digits. And then you have to ask yourself, are those digits meaningful? So I recommend you think very hard about what is the number of digits I should have in my table and only put those in, which has a secondary effect that makes your table less crowded. So my students are often saying, no, we want 4 digits. It's like, fine. We ran the experiment. We don't know that there's 4 digits of meaningful accuracy there, so let's not put them in. So why statistics? Almost all experimental stuff in CS involves noisy data of some kind. So the whole point is we need to separate our hypothesized meaningful variations from the random variations that are caused by that noise. So the noise causes our results to change. So I have to account for what change did I see because of the noise, what change was because of my algorithm. Ideally, we want to show the difference in performance is statistically significant. Okay, and you should be careful when you're writing and talking about significant differences. Should mean statistically significant differences, which means you should test that and see where it goes. So my hypothesis, any scientific hypothesis should be stated, and then we should provide evidence for or against it and conclude whether or not it's supported or refuted. Okay? As a hypothesis, it should be precise, explicit statement, and falsifiable. Right? Because again, experiments can only falsify things, they can't actually prove them. We then want to run experiments to confirm or refute it, and ensure the experiment really tests the hypothesis. This last part is outside the scope of statistics. This part here comes down to what we want to do with statistics. So when we want to elaborate our hypothesis, it might be something we've seen the slide before, right? Something that is good for task X, better than rivals Q and X for task R. We can say better according to behavior, convergence, efficiency, coverage, a range of things. Evidence can be theoretical, experimental, or both. Theorems are proofs, but experimental evidence is statistical testing on data. And you can easily have a paper that combines these. I actually, in lots of our papers that have theory, we almost always have theory for some piece and experiments to prove that theory actually relates to the real world. I have lots of papers where there is no theoretical proofs. There might be an underlying core theory idea, but there's no proof of it because it's too complicated to prove. You just do experimental analysis. So let's talk about non-statistical hypothesis testing. Okay, so a criminal trial is an example of hypothesis testing without statistics. In a jury trial, we must be between two hypotheses. The null hypothesis in the United States, H0, the defendant is innocent. Innocent until proven guilty. That's what we say. The alternative hypothesis, the defendant is guilty. The jury doesn't know which hypothesis is true. They must make a decision based on the evidence presented. So in the language of statistics, the defendant, convicting the defendant is called rejecting the null hypothesis in favor of the alternative. You've shown me enough evidence to reject the hypothesis they're innocent to decide that they're guilty. That is the jury saying, the jury acquits. We say there is not enough evidence to support the alternative hypothesis. So the jury is not saying the defendant is innocent. This maybe I use this as an example because this might help you keep track of what we're doing in statistics. The evidence doesn't show the person is innocent. There was just not enough evidence to show they're not innocent. Not innocent doesn't make you innocent. There's simply not enough data to show that you're innocent. You may be innocent, you may not be innocent. You might be guilty, but we can't tell to sort of see where they go. So, and this helps us understand the type of errors. And part of this is going to be great for Heather. There are two possible errors. A type 1 error occurs when we reject a true null hypothesis. That is, a type 1 error occurs when the jury convicts an innocent person. The null hypothesis was they were innocent. If we convict an innocent person, then that's a type 1 error. And we would like the probability of that type 1 error to be very small, maybe 1 in 1,000 or smaller, right? Which is what we might call beyond a reasonable doubt. So in fact, in trials in the United States, we actually have two standards of evidence. So in criminal trials, you have to convict with the beyond a reasonable doubt is necessary to convict. In a civil trial, the standard of evidence is a preponderance of the evidence, which is a weaker criterion. And the reason we do that is because in a civil trial, it's really about who's paying for whatever, right? And the errors are not as strong. In a criminal trial, somebody might get a death penalty, go to prison for a long period of time. We want to make very sure we don't have type 1 errors, because our presumption is people are innocent until we show they're guilty. In criminal cases, we want that to be very high standard. So I can talk about the probability of a type 1 error being alpha when I run my experiments. And generally, we want to design an experiment so that alpha is small, between 0.05 or 0.01. So we want to do a test and say the probability that I incorrectly reject a null hypothesis is pretty small. So that's where we're going to go with that. So what we call a type 2 error occurs when we don't reject a false null hypothesis. This occurs when a guilty defendant is acquitted. So the null hypothesis is they're innocent, they're actually guilty, we get it wrong and we let them go free. And in the United States, our criminal system is really set up to make sure this is the error we make more often. Right? We rarely want to convict innocent people, even if that means that sometimes guilty people go free. So if we test the hypothesis from a medical point of view, it may not be the same. If we test the hypothesis, the amount of medication in a heart pill is equal to the value which will safely cure your heart problem, and except the null hypothesis, this amount is okay. Later on, we find out this amount of medicine is way too large, and are people dying from too much medication, right? So that is, our null hypothesis was that was an acceptable amount of medicine. Now to not reject a false null hypothesis is problematic because people die from it. Right? So it's not always the case that you want to make sure that you have a low probability of a type 2 error. We often have to look at what is the risk of a type 2 error versus what is the risk of a type 1 error. So in standard statistics stuff, a type 1 error is generally denoted by the Greek letter alpha, and the probability of a type 2 error is generally called beta. These two probabilities are generally, and I should have put inversely there in quotes, inversely related. For a fixed sample size, decreasing one increases the other. Actually, it's non-decreasing. So if I decrease this one may stay the same or get larger, but it never goes down. Right? So there's a monotonic relationship between them, not quite inverse like 1 over x. It's just if one gets larger, the other gets smaller. So there's a trade-off between them. So in other words, you can't force both eta and beta to be really small for any given sample size. How small alpha and beta can be for a sample size is a function of the effect size, or sorry, the effect size, but we can't control that. You may either have to take a much larger sample, or in the court case, you may need more evidence to drive one or the other one down. Right? So the size of the effect, the variation you expect to see, depends on your problem. The only two things you're going to then deal with are what is the errors you're willing to live with and what is the sample size. So if I want to reduce these two, I have to increase the sample size to get things to work out. So one important thing about this that you need to get straight is type 1 and type 2 errors are defined based on the null hypothesis. Type 1, we incorrectly reject the null hypothesis. Type 2, we fail to reject the false null hypothesis. So, we'll use an example of, let's say I'm building an anomaly detection system. So what's a type 1 error?
So it depends on how you're defining it. But
okay, so that's what you're looking for.
So let's say that what we're saying is that we want to prove that this is an anomaly. So when it's not an anomaly, we identify it as an anomaly would be a type 1 error. And when we have anomaly that is identified as not, then it's a type 2.
So, but the answer is, I can define anomaly detection where my null hypothesis is it's an anomaly.
Right.
Or another one where my null hypothesis is it's normal, and anything that's not normal is an anomaly. So you can design your hypothesis either way.
Right.
And you can design your experiment either way.
So isn't this why we should show the confusion matrix?
So showing a confusion matrix between the two categories can be useful, but from a statistical point of view, you have to say, what is it I'm trying to prove?
You have to define your alpha and beta.
Right, so actually, I have to define my hypothesis. So
Right.
when I said the problem of anomaly detection, I didn't say my hypothesis. If my hypothesis, I've modeled the normal data, and I want to reject the hypothesis that this data is normal, then I get one kind of problem. If I want to say, I'm saying, I'm going to tell you when it's an anomaly, and everything else is not an anomaly, then I get the opposite. And the important thing about recognizing this is the alpha and beta literally just swap labels. If I swap the sign of my thing. So you can't force them both to be small, right? You can live with one or the other being where it is. But how you define your problem is critically important. So there are two critical concepts here. There are two hypotheses, the null hypothesis and the alternative hypothesis, right? And we're going to, the only thing we can do with statistics in our experimental design is reject the null hypothesis. When I reject the null hypothesis, I accept the alternative. And this often leads to things that are somewhat confusing. We'll go through a bunch of this in a second, right? So we're going to assume the null hypothesis is true. The goal is whether to determine there's enough influence to infer that the alternative hypothesis is true or the null hypothesis is not likely to be true. This is actually all we can decide, okay? And one of the problems we'll see is that there's a lot of people that end up making a false dichotomy. So they write down a null assumption, and they say the alternative assumption is something that actually isn't the opposite. And then you get into all kinds of problems. We'll see an example in a bit. So there are two possible decisions. Conclude there's enough evidence to support the alternative hypothesis and reject the null hypothesis, or conclude there's not enough evidence to support the alternative hypothesis, and we fail to reject the null hypothesis. Okay, my recommendation is when you're talking about statistics, when you're thinking about it, right, use the phrasing in red. The others, that'll keep you clean. I either reject the null hypothesis or I fail to reject the null hypothesis. Because that'll focus on what the experiments are really doing. The accepting this, the alternative hypothesis, is what gets people in trouble. Because if the alternative hypothesis isn't the opposite of the null hypothesis, because you're never testing the alternative hypothesis. You're only testing the null hypothesis. Everything is tested, rejected or not rejected. And then you can be a little clearer in what you're going to happen. So the two hypotheses, the null hypothesis and the alternative hypothesis, or sometimes the research hypothesis, the usual notation is that H0, which you can read as H naught or H null, is the null hypothesis. And H1 is the alternative of the research hypothesis. The null hypothesis always states the parameter equals the value, right? And the specified in the null hypothesis. So when I'm looking at this, right, a common way of looking at this is to say, I expect the mean to be this, right? And then the null hypothesis, that's the null hypothesis. When I reject it, the value is not equal to this. And here I just said equals, right? The parameter may actually be less than or equal. There's a couple of side tests we'll talk about, and we'll see how that goes. But so again, going back to that, then the two decisions, I can test that I reject the null hypothesis, or I can conclude there's not enough evidence, right? Note, we do not say that we accept the null hypothesis, especially if there's a statistician on it, right? We never accept the null hypothesis. We fail to reject the null hypothesis. And this is the other place that people dealing with statistics get themselves in trouble. They try and make the thing they want to be the null hypothesis. So we have a student whose thesis, right, he wanted to say there's no difference between what I'm doing and what human optimizers do. I can do as well as human operators. But you can't phrase your null hypothesis then as there's no difference between me and the thing, because all I can do is reject that, right? So what you really want to say is humans are better than me, or humans are different from me. And then if you say humans are different from me, and I can reject that hypothesis, then you can say, right, not that we accept the null hypothesis, you've now flipped it around, which leads to sort of inverted logic. If I want to have my experiment say X, my null hypothesis should be not X. Then I can reject the null hypothesis and get X. Because all I can do is reject the null hypothesis, or I can fail to reject it. It leads to some odd phrasing sometimes where you're trying to reject what you think is the thing you want to show. Sorry, but you want to reject the opposite of what you want to show and get that together. Does that make sense, or did I just confuse you?
No, that makes sense. But it also implies that you don't actually really prove our alternative hypothesis. All the way through is that there's enough evidence to support it.
Actually, no, you don't prove there's enough evidence to support the alternative hypothesis. You prove there's enough evidence to reject the null hypothesis.
Right. Which implies that there is some evidence to support what your real target is.
Well, so the tricky part there is the connection between the null hypothesis and the alternative has to be
complete and absolute opposites.
Right. So you know, if I say, for example, my null hypothesis is A, and my alternative hypothesis is C, right? Proving not A does not prove C. It proves not A.
Right.
So
my null hypothesis is that something isn't A, and I know that B and C is A. I've neither proved B nor C.
Right. Even if I say, for example, my algorithm is better than...
It's not better.
Is not better, or sorry, my algorithm is not better than this algorithm, right? And I reject that null hypothesis. Okay? Then I can say that my algorithm is better. If I say my algorithm is no different than this algorithm, right? And I reject that, then I know my algorithm is different. But I don't know if it's better or worse. So you can do a statistical test to say, there's a significant difference between my algorithm and this algorithm. Mine's worse. That's not what you really wanted to prove, right? So that's why I said you have to be very careful how you phrase these things, because when you reject them, you might say, well, I know my algorithm is better than theirs, so I'm going to make my null hypothesis there's no difference. And then I prove there's a difference. That doesn't prove that you're better, it just proves there's a difference. And we'll see what that shows up when we get to the statistical testing stuff. So be careful how you phrase this and work through really the not is that important piece of what you're going to do, the negation. So if the data are, so we're going to basically have two things, the statistical testing and random noise. If based on some random noise assumptions, right, if the data is not consistent with a null hypothesis, then I can reject it in favor of something else, which is really what we want to do. Or the data is consistent with the null hypothesis, then we can't reject it. Okay? And again, beating this up one more time, you can't say that H0 is true. You can always decide to reject or not reject. So when we talk about statistics, we will talk about something called the p-value, which will show up a lot when we talk about this. So the p-value is the probability that our result, for example, a difference between proportions or some ratio we're going to look at, or more extreme values could be observed under the null hypothesis. So if I ask, if I ran this experiment with random noise 100 times, the p-value should approximate how often I would reject the null hypothesis, right, given just the random variations. Okay, so when we talk about rejecting the p-value, we will generally talk about rejecting it at a reported p-value, or I will say we reject it with a p-value of some number. Again, not a lot of digits, just 1 or 2. Or I can say I'm going to reject it with a p-value less than 0.01, which is common. 0.01 and 0.05 are the two most common, 95% and 99%. So low p-values, low degree of compatibility between the null hypothesis and the observed data. The association is unlikely to happen by chance. You reject H0 and the test is significant. P-value says how significant it is. For high p-values, we have high degree of compatibility between H0 and the observed data. So the association is more likely to happen by chance. So you can't reject H0. The test is not significant. So high p-values are anything greater than 0.1. 0.05 is normally the cutoff between high and low, which doesn't really seem like high, greater than 0.05. High p-values of about 0.6, 0.5, 0.9, forget it, these variables are very tightly coupled, right? 0.01 might actually, 0.01 is generally considered significant. 0.1 is not significant, but it might be if I had more data. Because my test is based on, the association is likely to be by chance based on the observed data. So if I only give you 10 samples, I might have a high p-value. I might have 0.1. I will tell you, if you get an experiment where you get moderately small but still above chance p-values, ask yourself, what happens if I double the amount of data? Okay? Conversely, if I have a lot of data, hundreds of samples, and my p-value is not small, then don't worry, you're not going to get there.
Is there a relation between p-values and Pearson correlation coefficients?
There is under a particular model of what you mean by association. So Pearson correlation values tell me the slope of two interrelated variables. And if I'm asking the hypothesis, is variable 1 linearly correlated with variable 2? Then the Pearson correlation, 1 minus the Pearson correlation is the p-value. No, I got to divide by something. I divide by the number of data.
Because I've always seen, okay, Pearson correlation with p-value. That's what I've seen. Okay.
So I can tell you. So I can tell you the p-value of it, which basically is properly normalizing it by the number of samples.
Right.
So we have to divide by n settings.
We have to divide appropriately, and we'll get to what you divide by depending on what assumptions you're making and some other things. So the answer is not just divide by n. It is, for some tests, it is pretty much divide by n. For other tests, divide by n plus 1. And then for a whole bunch of tests, it's divided by n times n minus 1, right? N squared, because it depends on how many interactions are happening among the variables. So the levels of significance, we pretty much need a cutoff. The most common, greater than 0.5 is considered reject. H0 is not rejected, not significant, and 0.05 H is rejected. But sometimes we'll do this with 0.01, depends on how it's like. So if I ran 100 experiments and I used 0.05, what do I expect? I expect to be wrong 5 times out of 100. So what is that telling me? Is that a type 1 error or a type 2 error? So it's type 1. So we want to say type 1 is how often do I incorrectly reject the null hypothesis, right? So this is saying the probability that I will reject the null hypothesis, right? So this tells us that 0.05 is telling us how often are we going to have a type 1 error. But we have to be careful, right? I actually find it much better to give the p-value rather than just a significant versus non-significant test. But not everyone agrees with that. There's a lot of people in the statistics world that say, no, we should just have an overall thing. So you'll find places where the limit for statistics was set at 0.05. There was a strong relationship, significant, did not reach statistical significance, or whatever. All these, right? I like things with a relation was statistically significant, 0.0361. They better have a lot of data, they have 3 digits. So 0.05 is an agreed convention, not an absolute truth, and as a statistician, Russell put in their book, right? Surely God loves 0.06 nearly as much as 0.05, right? The difference between 0.05 and 0.051, 0.05 and 0.06, right? There's small differences. So use your sort of intuition. If it's 0.06, it's probably approaching significance, but the experiment didn't have enough data. Now, if you have 0.06 and you've run 1 million samples, okay, then maybe it's just not there. So 0.05, so this comes back to what I was just talking about. H0 should not be rejected, but it was rejected. That's a type 1 error. And H0 should be rejected, was not. That's our type 2. So if I go back to the truth and the decision based on the p-value, so if I have something where there is no difference, and based on the p-value, I say there's no difference, and I've made the right decision, and I make that 1 minus alpha of the time. If I say there's no difference, but the real probability is that there was a difference, that's my type 1 error. My type 2 errors occur when there is a difference. H0 was to be rejected, and it wasn't, and so that gives me my beta. And if there is a difference, there's supposed to be, that's the right decision, I get that 1 minus beta time. Right, so this sort of table puts them into sort of look at the truth and what you decided based on the p-value. Notice the decision here, although I asked about this before, the p-value itself does not directly determine either one of these. Right? It's related to the decisions, but how often these happen depend on which column we're going to look at and some model assumptions we'll come back to in just a little bit. So here's what we've already seen before, right? This is the jelly bean cartoon, right? So we run this experiment, right? So we ran it 20 times, and green jelly beans like to act in 95% confidence, right? If I ran it 20 times, then at 95% confidence, I expect one of them to be wrong. That's the definition of a 95% confidence interval. So just because I ran the experiment a whole bunch of times, I actually get this problem that I need to understand what's going on, right? So if I do repeated tests like this, which is what we really did here, right? We ran a bunch of tests that are not completely independent. We just did a test. There's something we're going to talk about a little bit later called Bolferi corrections to test for this. Now, the problem is you won't see this when people have done it in the research. They might have had a whole bunch of hypotheses, and they never reported any of these until they get the green jelly bean. Right? So you don't know what a researcher did. Well, I tried this, I tried that, I tried this, I tried that. They may or may not report them all. Yourself, be very careful what you're willing to do in running experiments. Don't run, I tried this test, I tried that test, I tried this test, because you're just confusing yourself. If you run 100 of them, you're going to get some of them that randomly happen to be true if you're running a statistical test. So we're now going to start talking about particular tests. 20 minutes. Yeah, we'll do the first couple. We won't go through them all. So the hypothesis testing procedure are really broken down into two main categories: parametric and non-parametric. So either they have parameters and they make parameter assumptions about the distribution of data, or they don't make. So parametric is not. Sorry, parametric is not do they have parameters, but do they make an assumption about the underlying distribution in a parametric form, or do they not make assumptions about the underlying distribution of data? Both of those are. So the z-test, the t-test, the ANOVA one way, we'll get through two or three of these, and then the non-parametric Wilcoxon sum rank test and commercial wireless H test. These are probably the 5 most common. We'll do a few more beyond these as well. So parametric test procedures are pretty easy to understand at a certain level. They basically involve population parameters. So if I assume everything is a Gaussian, then I can talk about the mean, okay? And I have some stringent assumptions. I've assumed it's normality. So this is the most common set of parametric tests. And example tests that fall into this are the z-test, the t-test, and the chi-square test. All 3 of these, and one more, sorry, the f-test. Okay, so now, before I go too much further, I don't remember how much you guys know about statistics and probability. Everyone have probability before? Yes?
Yes.
Somebody else?
20 something.
So
30 maybe.
does anyone have an idea why using the Gaussian or the normality assumption might actually be reasonable? Ancient probability stuff? Hmm? Well, so there's actually 2 things from probability that show up. So the first is called the strong law of large numbers. And this is related to central limit theorem, which is the second. So if I look at the difference between a variable and its mean, so I take the mean, I have a bunch of samples and I take the mean of them. And I look at the distribution between a variable and that mean. Okay? With a large number of samples, it will always be Gaussian. In fact, the central limit theorem says it converges to be a true Gaussian. So if I look at not just the mean and the value, right, the population mean, but the difference between variables and their mean, that distribution for large enough samples is going to be Gaussian. And it doesn't matter what the underlying distribution of the values are. The difference between the mean and the values becomes Gaussian in large enough samples. With some few assumptions. For example, binary variables never really have that property. 0, 1, 0, 1. They don't approach it. But the mean of a distribution of zeros and ones is some number between 0 and 1. Right? So it's always in the middle, but it doesn't always follow Gaussian. But all of these tests are basically exploit that fact of the strong law of large numbers. So non-parametric tests are very useful because they don't involve probability parameters. I forget to go back. So the strong law of large numbers, though, only applies to the difference between the mean and the value. If I actually want to talk about the value, those distributions could be anything. Non-parametric tests are more useful when we apply them to actual values instead of differences between the value and the mean. So the probability distributions here are anything I want to do. So I don't have to assume things. I make less things about independence. A number of these tests assume, well, they generally assume 2 things. They almost all assume what's called stationarity, which means my signal doesn't actually vary. Right? So imagine that I look at something that changes versus the time of day, and I sample it at a particular time of day. Well, that distribution is not the same as if I sample it later in the day. So there's a non-stationary property I have to assume. I can generally make non-stationary things stationary by what's called mixing. I basically take a bunch of them and mix them together and I lose time. Now they become a little bit better. If there's a dependent variable, I have to be very careful. Obviously, the value of sine of x is not a random variable, even though it keeps varying. And so I want to be careful what I look at. The nice thing about non-parametric tests, the data can be measured on any scale, a ratio, an interval, ordinal, or nominal. So I don't have to assume variables that I can subtract in metric space, which is how we get to means. And I don't have to assume that it's a linear metric space, which is really what undersigns that we're going to do with Gaussian. So some examples of this, which we'll go through, are the Wilcoxon sum test. Okay. At the end of this class, I will expect you to know 2 of these tests and to be aware of what the others are. I don't expect you to be able to reproduce them. Right? So nowhere, even on the exam, will I actually say, what is the Wilcoxon sum rank test? Right? That's what Google is for. That is what coding libraries are for. But you should understand parametric versus non-parametric and their advantages and disadvantages, because otherwise you can't choose the right thing out of the library. So you should be thinking about what those things are. So, advantages to non-parametric tests. They can be used with all kinds of scales, so I don't have to worry about what my scaling effects are. one of the reasons, well, we'll come back to that, I guess, in a little bit. Right? So, in some senses, they are easier to compute. They make fewer assumptions, so they are generally more valid. They need not involve population parameters, so I don't have to make so many things. And the results can be as exact as you need them to be as parametric procedures, because the results are these p-values you're going to get. Right? But some of the disadvantages. So first of all, they can waste a lot of information. They're not as efficient statistically as the parametric models. If the rules for the parametric models apply, with the same amount of data, they can make decisions, hypothesis tests, more with better p-values than the non-parametric. So a p-value, this is why I want to be careful relating it back to alpha. If all of the assumptions are true, then p-values have a direct meaning. But one of the problems I can have in my hypothesis test, which is not directly relatable to the p-value, because the p-value says, given all these model assumptions, here's the probability of a type 1 error. Well, there's another reason for a type 1 error, which is your model assumptions are wrong. So I can't work that into what I get out of the p-value. So parametric models make all these assumptions, and then they can make a strong decision with them. Non-parametrics waste information. They're less efficient with their information. So they can actually be very hard to compute by hand for large samples. We're computer scientists, we shouldn't be worried about that. But I don't know anybody who can compute a Wilcoxon some rank test for 100 variables by hand. It's just way too complicated. Not hard, but in my view, they're very easy to compute. You write a couple of loops, you're done. They are less widely known, and they are, because they're less widely known, when you write about them, sometimes people say, why are you using that? Why didn't you just do a chi-square test? Right? Chi-square is going to assume Gaussianity. Unless you really know Gaussianity, I would still do the Wilcoxon sum test. So some parametric, so some parametric and non-parametric equivalents. So we're going to talk about the paired t-test. The non-parametric, that's a parametric one, assumes Gaussianity. The Wilcoxon signed rank test is the similar version in a non-parametric form, right? So two-sample t-test, Wilcoxon sum rank sum test, which is different than signed rank. ANOVA, there's a Kershaw Wireless test, right? So when you have two or more independent samples and the assumptions of ANOVA are not met, you can use this Kershaw Wireless test. It's a rank-based test. However, the KW test needs a whole lot more data because it's not making assumptions, and because I have more than one variable, the number of interactions grow, so does the loss of inefficiency. So, so this one I don't use near as much because very often when I'm doing multidimensional stuff, I don't have enough data, I'll use ANOVA. I'll actually use paired t-test and sample t-test a lot, but I'll also use the Wilcoxon sum rank test. It depends. I will use the paired t-test when I'm comparing variables to the mean every time, because the law of large numbers says the difference between a variable and its mean is well studied. So if I do things where I normalize properly by subtracting and maybe subtracting and dividing, right? I can subtract the mean, divide by standard deviation, I can do all kinds of stuff. But other times I will just use the paired t-test, even though I could have used the Wilcoxon sign rank test, because it's easier. It's built into Excel, and the Wilcoxon rank test is in the stats package. And more people know what it is. And if the p-values for the paired t-test are low enough, I'm not going to worry about it. So if I get near the boundaries, I might care. So let's look at t-tests. So the underlying question for a t-test is, I'm going to compare the mean between two different distributions. So if I have condition 1, the green condition, and condition 2, the blue condition, I want to answer the question, is there a difference between the means for green and blue? My null hypothesis is going to end up being there is not a difference. Oh, okay. So underlying this is that if the samples are taken from the same population, so if really green and blue should be the same, then the means of green and blue should be the same. Okay? If two means are statistically different, then it's unlikely that samples are drawn from the same distribution. Now notice things could be drawn from two different distributions and have the same mean. So if I have these two distributions, they might have the same mean, but they have very different distributions. So I might not want to decide that blue and black here are the same. This test cannot answer that question. It's only going to look at the means and answer, are the means.
Do we have to do tail divergence too?
Well, so the simplest idea of a t-test is just basically, if we include the variances, which we can get to, then we can do all kinds of things. So I just want to talk about what those are. But this comes back to the sort of hypothesis test, right? So notice now we've gone to the hypothesis that a difference in means says they are different distributions. Okay? So if the means are very different, chances are they really are different distributions. But if the means are the same, it doesn't mean they're not different distributions. Right. Related back to our test, right? So it turns out that the way we're going to actually do this actually will account for those, although I wanted to explain the difference and sort of explain why it's not there. We're actually not going to look at just the means. So the means are related to, and by the way, this is called a t-test because there's an underlying distribution called the student t distribution, which comes from the distribution of some differences between Gaussians. So I'm going to take the difference between the means, divide by what we call the standard error of the mean. So I'm going to look at the mean of x1 minus the mean of x2 minus the standard error of x1 and x2. And we'll get to what that's related to in a second. The standard error is like the standard deviation, but it's a pooled sample, so it doesn't have the same name. So we look at the differences and then normalize it by the spread of the data. You'll see why those come up in a second. So the formula for the standard error between x1 and x2 is the square root of the standard deviation of S1 divided by n1 plus the square root of the square. Sorry, the formula's there.
No worries.
Yeah, so we take the square of the standard deviations, or sorry, of the per element standard errors, square them, which gives us the standard deviation. N is the number of samples, right? And so you're normalizing them by how many samples are in each distribution, and that gives us the standard error. And so in the blue and black one I drew on the board, right, one of them will have a very large standard error, the other have a very small error. So then I'm going to be dividing by a large number. So
What was this one? It's just the standard
standard,
deviation? It can't
so-
be just the standard deviation.
yes, the standard deviation. So this is this, but this is combining standard deviations of the samples, right? It's not combining them by.
Shouldn't we multiply that then by something? We're dividing. I'm not sure.
Well, so should we? It depends what we want to accomplish here. So the division here, right, in these, the division here,
Greater weight.
right, is really just a weighted sampling. So this t statistic actually doesn't normalize by the number of points because the more points you have, right, the more points I have down here, the more points I have down here, right, the smaller these numbers become.
Right.
The smaller this number becomes, which makes the ratio more sensitive to small differences in the mean. And what it really comes down to is this is derived from the fact that if I have lots and lots of random samples, and I ask the question, if I randomly choose a bunch of points from here, randomly choose a bunch of points of here, and these distributions really were separate, how likely is it that the difference will be there?
Oh.
As I grab more and more points, as n1 and or n2 gets to be very, very large, then their means become very well stabilized. Right? They converge to the true mean very quickly. And therefore, I expect any differences in the mean that show up in the top to now become more and more significant. So you want it to normalize by n because you want to think, and I want it to not depend on it. It depends very strongly on n because we want it to.
So you're trying to force large n's.
So for large n's, a small difference in the mean is statistically significant because it shouldn't happen for large n's. So if I sample 1,000,000 times, right, there should be no difference in the mean if they're from the same distribution.
Right.
But if I only sample 10 times, the samples could have just randomly hit places and I can just expect there to be a lot more variation. So our goal is not to derive these, but that's a good intuition to recognize that more samples show up and make this more significant because these get large, which makes this number small, and dividing something by a small number makes it bigger.
How do we really suppose to use t sample?
So Should you use the t-test if the number of samples is large? Should you? Yes. Do you have to? No. So cheaper tests are available if you have a large sample size. So that's a question of which you want to use. Depends on what assumptions you want to use. I would actually say if you have a lot of data, I would go for the Wilcoxon test. Why? It's less efficient, but with lots and lots of data, you're not worried about statistical efficiency anymore, and it makes much less assumptions. The biggest problem here is this is assuming that the underlying distributions follow these properties, and they may or may not follow these properties. Although I am subtracting two means here, I have not said what the underlying variable was. If that variable was the difference between the variable and something else in its mean, then this is a good test. If it's really just the performance of my algorithm measured in milliseconds, maybe not so good, because it doesn't necessarily tell me what's going on. Right? Variations, differences from the mean will be good, but absolute values will be tough. Okay, so we're really just looking at how far apart are these versus what's the spread that they're dealing with. Okay, so there are two types of t-tests. Well, there's a couple more, but we'll talk about the two big ones. So the first way we break them up are two-tailed versus one-tailed t-test. So this comes back to my hypothesis. If my hypothesis is algorithm A is different from algorithm B, my null hypothesis is the two distributions are the same, and I'm just trying to say, is there a difference? Then this is what I'm doing. It's called a two-tailed test, right? There's a chance that algorithm A is better than B, there's a chance that algorithm A is worse than B, I don't know which it is. My test is just, are they the same? Another test, the one-sided t-test, says algorithm A is better than algorithm B. So here, if I have 5%, I'm looking at the area under just this part of the curve, ignoring this half. And pretty much for a t-test, if I say a two-sided t-test, my p-value is 1/2 if I say a one-sided t-test. So you can play games and sort of decide where it's going to go. P-value for one-sided is smaller than two-sided. So the choice of one-sided or two-sided depends on what I'm going to do. If my test is I have two populations, I should always be doing a two-sided t-test. If I'm comparing a known value, I should do a one-sided t-test. So if I have a survey where the middle is acceptable, and so I have five values, really bad, acceptable, good, very good, neutral in the middle, right? I can say a one-sided t-test, right? It's statistically above neutral. It's a positive sign. I'm testing a known value. If I have two sets of data, I should be doing a paired two-sided t-test. And then if I wanted to decide that A is greater than B, I can still say the mean of A is greater than B, and I have my two-sided t-test. But my test should still be two-sided. Okay, so why do we do a paired t-test? So if I actually have, and this plot might not show it really well, but let's say I have two processes, and the processes actually have a whole bunch of variation. That is, I run my process, and it can take anywhere between 1 second and 12 seconds. So the time could be very large. If I try and just do the paired t-test, a t-test, not a paired one, a regular t-test between two different algorithms with this large spread of data, I might not be able to decide there is any difference because the variation is very large. We actually saw that when we were talking about the examples in the last two classes. However, if I do a paired t-test, and I say, here's algorithm 1 on this piece of data, here's algorithm 2 on this piece of data. Algorithm 1 on this piece of data, algorithm 2 on the same piece of data, right? So now, if I look at the samples of paired distances, where I subtract them, I get something that's a much tighter distribution because I'm not seeing the variation caused by the normal variation of the algorithms on the amount of data they process. I'm just looking at the differences. So paired t-tests, whenever I can run and get the same output on the same input, then you should do paired t-tests or paired Wilcoxon test, Wilcoxon sign test. You want to pair them up because that reduces your variance if I let them all run. And so a classic example of this is to sort of think about if I have two algorithms, one of which this performance looks like that in terms of what the speed of the algorithm, and another algorithm looks like this. If I look at these from a pure t-test, with this mean and this mean, right, there's no way to decide that there's a significant difference, because there's so much variance. But if every one of these is actually paired up, if on every test, every single test, the black one is better than the red one, then that's significantly better, right? So, because the chance of that happening randomly, that almost everywhere black was better than red, that just doesn't happen randomly, right? If it was random variations, then you expect red and black to be crossing each other. So you can detect very subtle differences, or more subtle differences, with a paired kind of test than you would from a non-paired test. So when we get done, this gives us a sort of chart of two kinds of things, and actually given our time, because I want to go into the non-parametric versions next, we'll pick it up here next class. You know, you should have all, if you haven't checked on Canvas, I have provided some level of feedback for all of the papers. It's not a lot, unfortunately. I think I mentioned this last class. I lost a whole bunch of them, and I didn't feel like going back and doing them all. So I have read them with more detail than